This is Scout 1.3, Exponential Functions and Models. Okay, let's do a review of exponential functions. This is what a general exponential function looks like. A is the coefficient, some base b to the power of x. Now, we also have another exponential function that's sometimes used where we have the base of e, which is a constant now, still a coefficient a, but we have a constant on the x, which is called a rate. So here we would need to find the a and the b in order to complete this form. For this one, we would need to find the a and the r in order to complete this form. They both will produce the same results. When you graph an exponential function and you have, let's say, b is greater than 1, like the basis of 2 or 7 or something like that, what you'll have is a graph that is slow to rapid growth. Slow to rapid. Okay. And this is what we use for measuring interest rates, because the interest rates are slow to rapid. To get this equation to be slow to rapid, you would need to make sure that the r that's being used here, let's put it here, the r is greater than 0. Okay, basically a positive number. And if r is a positive number, then you have slow to rapid growth for this version. Let's say growth. Okay, now, what would happen if the b here was between 0 and 1? If b, the base here in this form, was between 0 and 1, you would have rapid to slow decay. And to get rapid to slow decay from this version of an exponential function, slow to rapid here, the r that's being used there would have to be negative. Less than 0 means negative. Okay, now let's look at some exponential properties. Property number 1, when you multiply common bases, the property is that you add exponents. Property number 2, when you divide by a common basis, you're dividing exponentials, the rule is that you subtract exponents. Numerator minus the denominator. The third property is when you have a base raised to a power, or exponent, and that is all raised to another exponent, the property is that you multiply exponents. The fourth property says that all roots can be converted into exponentials by using the inner power as your numerator and the index of the root as your denominator. And this will also go backwards and forward. You can turn an exponential into a root by using the numerator for the power of the base and the denominator for the index of the root. And fifth, a base raised to the 0 power will equal 1. Only if you don't have a base that's 0 already. You don't want to raise 0 to the 0 power. That's undefined. But any other number, you raise it to a 0 power, you will get 1. Now we're going to do a little bit of modeling. As a review, we've already done linear modeling, where we took 2 points and we created a linear equation that went through these 2 points, or that would represent This is input and this is output. Okay, and we did that by finding the slope. We did basically a keep and change. That gave us our slope. Let's say keeping -4 and then +16, keeping 2 and -4, and that gives us a 12 all over -2, which is -6. That's our slope, and then we put this into the slope, the point slope formula. So this would be y and the opposite of y, +4 equals -6, and then the opposite of x would be -2, and we get y plus 4 equals -6x plus 12. And then we'll subtract 4 from both sides, and we get a linear equation. Y equals -6x minus 4 gives us +8. This is the linear model for these 2 points. What we're going to do now is that we're going to get a model that's going to be an exponential model from 2 points. Okay, and there's 2 types. There's this model here that has A and B. There's another model that has A and R. Let's get a model that represents those 2 points that uses the A and B. So I'm going to use y equals ab to the x for this one, and y equals ab to the x again for that one. All right, this is the input, this is the output, or should I say this is the x, this is the y. So this will be, the y becomes -4, ab to the, let's see, x is 2. Now that I put my -4 and my 2 in here for x and y, I'm going to solve for a. Solving for a, I divide both sides by b squared, and I get -4 all over b squared equals a. Now from there I'll stop because we have solved for a. I'm going to go to that side, and I'm going to use the x and the y here, and I'm going to use the a from here. So I'm going to use 3 things. So this y right here will be -16. This a will be -4 all over b squared. Then the b, and the x here will be 4. Okay, now I want to simplify this. -16 equals -4 b to the 4th all over b squared. These two simplify to -4 b to the 2nd power, because we subtract the exponents. Then I'll divide both sides by -4, and I get 4 equals b squared. From here I'll take the square root of both sides, and we get b equals 2. Typically when you take the square root of both sides, you get plus or minus, you get 2 potential answers, but the b that we're using here is going to be a positive b. So we have b is 2. Now, with this answer, I'm going to go back here and put in 2 for b. So I have -4 all over 2 squared equals a. And so -4 all over 4 gives me that a is -1. So now, I have my a is -1, I have b is 2. So, I go back to my original. Y equals, well, let's use f of x. F of x equals abx. And for this model, the a will be -1, the b will be 2 raised to the x power. And this models a function that includes the points 2, -4, and 4, -16. Number 2, I want a model that goes through these 2 points that is exponential. So, I need to introduce y equals abx on both sides. Y equals abx on both sides. Then I'm going to replace this y and x with this y and x. So y becomes 1.2 ab to the 1st power. From there, I'm going to solve for a. So I'll divide both sides by b, and I get 1.2 all over b equals a. So a has been solved. Now, I will go to the other side, and I will take this model right here, this general form here, and I'll put in this number for y, this number for x, and then I'll use my a, which is 1.2 over b. So y becomes 0.108, the a becomes 1.2 all over b, and then we have b to the power of 3. Now I'll start simplifying this. So 0.108 equals 1.2 b to the third power all over b. This simplifies to 1.2 b squared. Now let's divide both sides by 1.2 as we solve for b. And I'll take 0.108 divided by 1.2. And we get a 0.9 equals b squared. Now I'll take the square root of both sides, and I end up with 0.3 equals b. So now I have b. So I'll go back to this side, and 1.2 over 0.3 for b is equal to a. This will give me 4 for a. And so now I have the a and the b value. And I go back to my model. F of x equals a b to the x. And I place in my a, which is 4. My base, which is, let's see, this kind of separate this with parentheses here. Parentheses 0.3 to the x power. Just to keep separation. And that's it. Number 3. Okay, we're going to do modeling based on this. So we'll have exponential modeling. So y equals a b to the x. Y equals a b to the x. Alright, from here, this is my x and my y. So I'll put in 2 for y, and I'll put in 1 for x. From here, I'm going to solve for a. So I'll divide both sides by b. I get 2 over b equals a. Then go to this side and I'll plug in 4 for x, 6 for y, and 2 over b for a. So what I have here is 6 equals 2 over b to the 4th power. Now I'll simplify this. 6 equals 2 b to the 4th all over b. If I subtract the exponents, I'll get 2b to the 3rd power. Divide both sides by 2, and we get 3 equals b to the 3rd power. Now, what I want to do, I can take the cube root of both sides. No, let's go ahead and do the cube root of both sides. This gives me the cube root of 3 equals b. Also, this can also be written as 3 to the power of 1/3, because 3 can be used as the denominator, and the understood 1 on the 3 can be used as the numerator. Okay, now that we have both of those, let's switch over here. We now have 2 all over the cube root of 3, and that's our a. So we have our a and our b. Let's go ahead and construct our model. F of x equals a b to the x, where a is 2 all over the cube root of 3, and b is, I'm going to use the 3 here to the 1/3. 3 to the 1/3 all to the power of x. Now, the reason why I did that is because I can combine these two and simplify this even further. So 2 all over the cube root of 3, and we have 3 to the power of x third. Because when you multiply 1/3 times x, let's go over here, 1/3 times x, you say 1/3 times x over 1, 1 times x is x for the numerator, and 3 times 1 is 3 for the numerator. So you get x over 3. Okay, number 4. We have here that bacteria grows, 1,000 bacteria grows to 1,500 in 2 hours. We want to find a model for this. So it means that we're going to need to know what's going to be input and what's going to be output. Typically, we want time to be the input what we want to be output is going to be the number of bacteria. So, we know that the bacteria will be 1,000, but at what time? Well, this is the starting time. It doesn't tell us what the starting time is, but the starting time is always going to be 0. So 0 at 0 time, we have 1,000. But 2 hours later, our bacteria count is now 1,500. So I have made points using time as input and bacteria as output to create an equation that would have time as input and bacteria as output that would model this situation. So let's start off with the generic. Y equals ABX. Y equals ABX. The 1,000 will be for Y. And we have A and B to the 0 power. B to the 0 power will give us 1. So this is A times 1. So here we have A equals 1,000. We'll go to the other side. I'm going to put 1,500 in for Y, 2 for the X, and then 1,000 for A. So this is 1,500 equals 1,000 B squared. Then we divide both sides by 1,000, and I get 1.5 equals B squared. Then I'll take the square root of both sides, and I end up with B equals the square root of 1.5. Now I have values for A and B. So typically I would say f of x equals A B of x. But this time I want to change the input and output to B's and T's. So this is the bacteria input time will equal A B to the T power. And now the function actually matches the language of the original problem. And let's put in the values. A is going to be 1,000, and the base is going to be, let's change that to 15 to the 1/2 power. So we have 1.5 to the 1/2 power. So let's put that on the inside, sorry. And all raised to the t. The reason why I did this instead of using the root is because I want to combine the t and the 1/2. And so we'll get 1,000, 1.5 t over 2 power. And this is our model for our bacteria growth. Number 5. If blood alcohol levels start at 200 and decrease to 150 in 1 hour, find the amount of alcohol in the blood after 4 hours. To find the amount of alcohol in the blood after 4 hours, we need an equation that models the alcohol decline. So we're going to create that model by getting values for input and output. So let's start here. I want to be able to output the blood alcohol level. So let's make that B, blood alcohol level. The input for finding that will be time. In the last case, it will be 4 hours. So time would be the input. So I know that the blood level starts at 200. So 200 goes here. Since this is the start, the time for that will be 0. Furthermore, 1 hour later, I'll have a blood alcohol level of 150. And the time will have passed within 1 hour. So I'm going to use this to find my model. So let's take let's use y. Y equals a b to the x, and y equals a b to the x. Okay, 200 will go in for y, and 0 will go in for x. B to the 0 is 1. 1 times a is a. So a is 200. Let's go to this side. I'm going to use this for my y, the 1 for my x, and the 200 for a. So this will be 150, 200, and a base to the 1 power. Okay, let's divide both sides by 200. Let's see, and I'll get 15 over 20, which is about 3/4. So I have an a and a b now. So, in general, we have f of x equals a, which is 200, and b, which is 3/4, all to the power of x. Now, since we're talking about blood and time, I'm going to change this to b of t equals 200, 3/4, and then t. And this is the equation that will model the blood, this particular situation where the blood is going down 1 hour to 150 from 200. Now the question is, what happens in 4 hours? Well, let's use this equation. B of t equals 200, 3/4, and to t. And now I want to put in 4 hours. So we have 200, 3/4, all to the 4th power. Okay, now it's going to get a little interesting. Let's see. 3 times 3 is 9, and 9 times 9 is 81. 4 times 4 is 16, and 16 times 16 is 256. Okay. Now, from there, let's take 200 times 81, and then divide that by 256. In 4 hours, our blood alcohol level will be 63.3. Okay. I want to redo this problem, but using this model here, where we have to find A and R. So, we have y equals a e to the rx, and y equals a e to the rx. The y is 200 here. We have a, e, and r, and the x will be 0. So we have 200 equals a e to the 0 power. E to the 0 power is 1. So we have a times 1, and a is 200. Then over here, we're going to put a in for 200, this for y, this for x. So 150 equals 200 e to the power of r times 1. Okay, so we have 150 equals 200 e to the r. Okay, divided both sides by 200, we end up with, let's see, 3/4 equals e to the r. Now to solve for r, we're going to use a rule of logarithms that says we have the natural log of 3/4 on this side will equal the r on that side. So the natural log of 3/4. That's going to be a decimal. I may just leave it as a, well, let's find out what it is. ln 3 divided by 4, and yeah, a lot of decimals. So we have a negative 0.287. Okay, so this means that our function now is b of t equals a, which is 200, e, and the r, which is negative 0.2877, and then instead of x, we're going to do a t. That's our function. Now, before, we were using this, so now let's change this into 200 base e to the power of negative 2.877t, and we're going to put in 4 hours. So 4 hours inside this equation will give us negative 2.877 times 4. Okay, I'll have to multiply all this by 4. So times 4. And my new exponent will be e to the negative 1.1507. Okay, now I'm going to type in 200 times e. Let's see, e is going to be second function natural log raised to the power of negative 1.1507 and enter. And what I get is 63.3. The same solution.